Hello, thank you for watching this video. So on this video, I'll be doing question 5 of November 2020 question paper, Physical Sciences paper 1. So I'll do question 5, all of it. I'll start with question 5.1 up to 5.4. I'll also upload or show the question paper on the screen as I'm reading it. So I don't have a printed version of the question paper. So what I will do is I'll read from the laptop, but you'll be able to see it as I'm reading. So question 5 reads as follows. A roller coaster car of mass 200 kg with an engine switched off travels along a track ABC, which has a rough surface as shown on the diagram below. You can see the diagram. At point A, which is 10 meters above the ground, the speed of the car is 4 meters per second. So what they are saying, you have this roller coaster car with a mass of 200 kg which is switched off engine, travels along a track ABC of a rough surface. So at point A, which is 10 meters above the ground, the speed of the car is 4 meters per second. So you got that information. Let's continue. At point B, which is height h above the ground, the speed of the car is 2 meters per second. So at point B, the speed of the car is 2 meters per second. During the motion from A to B, 3.4 times 10 to the power 3 joules of energy is used to overcome friction. So as your car moves from point A to point B, an energy of 3.4 times 10 to the power 3 joules of energy is used to overcome friction. Ignore the rotational effects due to the wheels of the car. So we have this information here. So I'm going just to try to break it down. So we have this roller coaster car with a mass of 200 kg. Its engine is switched off, so there's no force applied by the engine. It travels from on the track A, B, and C on a rough surface, which is there is friction between the car wheels and the surface. At point A, where it starts, it is 10 meters above the ground and has a speed of 4 meters per second at point A. At point B, which has the height of h above, so above the ground, which have the height of h above the ground, has a speed of 2 meters per second. So at point A it was 4 meters per second the speed. At point B the speed is 2 meters per second. During the motion from point A to point B, an energy of 3.4 times 10 to the 3 joules is used to overcome friction. So this is the energy lost due to friction from A to B. So let's go to the questions. Question 5.1. Question 5.1 reads as follows. Define the term non-conservative force. More like they're asking, what is a non-conservative force? A non-conservative force is a force which the work it does depends on the path taken. So the amount of work done by that force depends on the path taken. The longer the path, the more work is being done by that force. So, as I said, the non-conservative force is the force at which the work done depends on the path taken. So let's define it. So it's a non-conservative force. The force which the work done by it depends on the path taken. So that's a definition of a non-conservative force. A non-conservative force is the force at which the work done depends on the path taken. So let's go to question 5.2. 5.2 read as follows. Calculate the change in kinetic energy of the car after it traveled from point A to point B. So they want us to calculate the change in kinetic energy of the car from point A to point B. As you might know, if you want the change, which means it's final minus initial, so you must have the final kinetic energy and the initial kinetic energy. Then you find the difference between the two. That's how you find the change. If you want to change in velocity, it's final velocity minus the initial velocity. So that's what we are going to do here. So if you want the change in kinetic energy, it's going to be EK final, right, minus EK initial. This is how you find the change, right? So it's change in EK is equal to EK final minus EK initial. This is how you do it. And you know, so now you must calculate the final kinetic energy and the initial kinetic energy. So you know the formula of the kinetic energy. EK is equal to half mv squared. So where your m is your mass and your v is your velocity. So you are told that at point A, which was our initial point, you are told that the velocity was 4 meters per second. At point B, you were told, which is the final point, you are told that the velocity, which is the final velocity, was 2 meters per second. So you know the mass does not change, it was 200 kg. So the only thing that you are going to do is calculate the final kinetic energy, which is now just m, which is 200 kg, put in your plug your final velocity and find the final kinetic energy. Do the same thing for the initial kinetic energy. Then once you have done that, calculate the individual energies, the final and the initial. Just find the difference between the two. Then you'll get your change in kinetic energy. So let's do that. So what we're going to do here, we're going to say, okay, EK initial is equal to half m v initial squared, which is equal to half, your m was your mass of 200 kg, your initial velocity was 4 meters per second squared. Then you find this, the value of this. So use a calculator, half of 200 times 4 squared, which is 1,600 joules of energy. Same thing, go find the final kinetic energy. So you're going to have EK final is equal to half m Vf squared, where Vf is your final kinetic energy. So it's going to be half of your mass, which is 200, times final velocity, which is 2 squared. So plug this on the calculator, half of 200 times 2 squared, which is 400 joules of energy. So you said you want the change in kinetic energy. So to find the change is equal to change in EK is equal to EK final minus EK initial. So you have your initial kinetic energy, your final, to be 400 joules minus 1,600 joules. So your change in EK is equal to 400 minus 1600. That is negative 1200 joules of energy. This is a change in kinetic energy. I hope that is clear. So, now we go to question 5.3. So, question 5.3 reads as follows. Use the energy principles to calculate the height h. So, they want you to find the height h. So, to do this, here, so you're going to use your energy principles. So now, on this, from point A to point B, you have a non-conservative force there. Your non-conservative force, the only non-conservative force that you have here is frictional force. And you know that the work done by the non-conservative forces, 5.3, the work done by non-conservative forces is equal to the change in EK plus the change in gravitational potential energy. So, luckily we have calculated what the change in EK is. So this is what we need, the only thing we need. But for the sake of making this very clear, I'm going to redo the entire calculation so that you understand why, so you can be able to redo this question in case it's asked again without you being asked this part of the question. So let's go. So the work done by non-conservative force, which is your friction in this case, is equal to, so they want you to find the value of h. So the work done by non-conservative, which is the work done by friction. So you were given the work done by friction because you were told that on the statement. Let me go back to our original statement. So you were told on our statement that during the motion from A to B, 3.4 times 10 to the power 3 joules of energy was used to overcome friction. So that is work done by that non-conservative force, which is friction. So you have this part. You have this part. So now you only need the height, which is here. So, but let's go through this. So the work done by non-conservative force, which is friction in this case, is equal to change in kinetic energy, which is EK final minus EK initial plus EP final minus EP initial. So this is your gravitational potential energy. So we continue. We say, okay, work done by our non-conservative force is equal to EK final, which is half mvf squared. We have done this already. Minus half mvi squared. We've done this part already, which is part of Usho's 5.2. Plus EP gravitational potential energy, final part, which means now the final part is at point B, this part. Same as here, because the final velocity that we used was that of point B, and the initial was that of point A. So the final part of the gravitational potential energy is that at point B, and the initial part is that at A. So this is mgh, which is the final height, minus mgh, the initial height. So now we can start substituting the values that we have. So here we were given the work done by non-conservative force, which was the work that was used to overcome friction. And friction in this case is our non-conservative force. I'm not sure if that makes sense. So friction is a non-conservative force because the work done by friction depends on the path taken by the object. So the work done by friction is defined by the path taken by an object. So now we are given that the work done by friction is negative 3.4 times 10 to the minus 3. One must be wondering why it's negative. So friction is opposing our motion. So the work done by frictional force will be negative. Okay, so since you have calculated the change, you can just directly put in that negative 1200 joules. But in case in future they don't ask that question first, I want you to know how to approach this question. So our mass is what? 200 kg. In our bracket, what do we have? We have we have final velocity, which is 2 squared, minus 4 squared, which was our initial. So what I've done here, I've taken out m as a common factor. You are left m and half as common factor, half m as common factor, which is this. Now you're left with vf squared minus vi squared inside the bracket, plus. So here your mg are your common factors, your m and g. So we have m, which is 200, times g, which is 9.8. Inside you're left with final h, which is what you're looking for. H minus your initial h. Your initial h, you were told that at a it was 10. So that is what you are looking for, this part here. So what you can do is to punch this on your calculator and that. So we know that it's negative 3.4 times 10 to the, oh sorry, it's positive 3, right? Yeah, it is positive. It is positive 3, sorry. Equal to this, we calculated this and we found that it was 1200 joules. You can punch it again. Plus 200 times 9.8. 200, which is this part here, times 9.8, which is 1960, times height minus 10. This is our final height. Take this to the side, transpose this to the side, which is now going to have negative 3.4 times 10 to the power 3 plus 1200. That gives us negative 2200. Negative 2200 is equal to 1960. H minus 10 divided by 1960. Divide by 1960. This and that, they are gone. You are left with this divided by 1960. And it's positive. Why did I make it negative? 1960. Which will give you negative 1.12 is equal to h minus 10. Then you transpose the 10. So you have 10 minus 1.12 is equal to h. And your h is equal to, just punch this in your calculator, which is 8.88 meters. So that is your height at B. Therefore, h is equal to 8.88 meters at B. That's it. Then you move to the next question. Of question 5. Let's go. This question reads as follows. On reaching point B, the car's engine is switched on in order to move up the incline to point C, which is 22 meters above the ground. So now, when this car of yours gets to point B, the engine is switched on so that it can move up the incline and reach point C, which is 22 meters above the ground. So now there will be an applied force now at this point. But let's continue, because the engine will be applying the force. While moving from point B to point C, the car travels at a constant speed of 2 meters per second for 15 seconds. Let me read this again. While moving from point B to point C, the car travels for 15 seconds at a constant speed of 15 meters per second, while an average frictional force of 15 newtons acts on it. So now, as the car travels from point B to point C, it travels for 15 seconds at a constant speed of 2 meters per second, with experiencing an average frictional force of 15 newtons as it goes up the incline. Okay. Now the question says, calculate the power delivered by the engine to move from point B to point C. So they want you to calculate the power delivered by the engine to move from point B to point C. So now, in order to approach this question, you need to understand what is power, because you can't solve something that you don't know. Okay, let's do this. So power is the rate at which work is done, or the rate at which energy is transferred. That's power. Power is the rate at which work is done, or is the rate at which energy is transferred. By that we mean power is work over time. And you know that work is called force times delta x cos theta, which is work over time. And you know what this thing is. So you can also say F cos theta times velocity, because this is velocity. So this is how you find work. Is the rate at which energy is transferred, or work at which work is done. So now they're saying calculate the power delivered by the engine. So they want to calculate the rate at which work is done by the engine. So you need to know how much work is done by the engine. Then once you know that, you can find that rate by dividing the work done by the engine by the time it takes to get to the top. Or you can find the force applied by the engine multiplied by the velocity. Force applied by the engine multiplied by that constant velocity of your engine. Applied by your engine. So now, to do this, this is what you can do. So you are told that the car travels up the incline for 15 seconds at a constant speed. What does this mean? So if you're saying you have a constant speed, right? What does it tell you? It tells constant speed. This means that your acceleration is 0 meters per second squared. So this object is not accelerating. And you know that F net is called ma. So from this, what you can say is, okay, if you know F net is called ma and your speed is constant, your acceleration is 0, that tells you that your net force is 0, right? So, and you know that the work net, which is, when you say the net force, which is the sum of forces acting on that object, is 0. When you say the work net, which is the sum of work done by the forces, is 0. So now your work net will be your F net times the displacement. So now, if you're saying your speed is constant, right, that means your object is not accelerating. Your acceleration is 0. Because this, your acceleration is 0, right? So if your acceleration is 0, your net force is 0, because the net force is equal to the mass times the mass of the object, which is 200 kg, times the acceleration, which is 0. So your net force is 0 newtons. And if your net force is 0 newtons, that means your work net is also 0, because the work net is equal to the net force times the displacement. You know that the net force is 0, which means your work net should be 0 joules. So this is the information that you should be knowing. So once you are given that the speed is constant anyway, you should know all this information that is provided here. All this information that I just provided here. You should be knowing it. If you didn't, it's fine. I'm sure you can know it from here. That's the most important thing. And that's why it's good that you watch this video. Okay, now let's continue. So what we need the most is the work done by the engine. Right? So, you are told that we did calculate on the past video and said, okay, the drawing was something similar to this. So you had your A here, you had your B here, you have your C here. And you were told that if this is your ground here, this distance here is 22 meters. This distance here, you were given, it was 10 meters. And this distance here, we calculated it. We found it was 8.88 meters. Right? So now, what you need to know is that now you are working on this incline here, which is this one here. So your height is no longer this whole 22. It's going to be 22 minus your 8.8, which is now, you are working on this triangle here. So you need to remove this and know that you're working only with this triangle that is here. Because what we need to find the force applied, or the work done by the applied force. That's what we need. The work done by the applied force, so that we can divide it by our time to get the rate at which the energy was transferred, or the rate at which the work was done. So let's continue. So to do this, you say, okay, you will need to have, so we first find this height here. Our height is 22 minus 8.88, which is 13.12. 13.12. This is the height here. So this is where we will be working on mostly. Now, this does not really matter. So from this point, you say, okay, the work done by the applied force. You will need to have you will need a free body diagram of the object between B and C. So when this object was between B and C, this is how the free body diagram looks like if it's sitting here. You have the normal force acting on it. You have gravity acting on it. You have the applied force, which is the force of the engine. And you have the frictional force acting on it. These are the four forces that are acting on this. So you want the network. The network is sum of the work done by the forces. And you know that the only forces that do the work are the ones that are parallel to your surface. Those that are perpendicular to the surface, it will be cos 90 degrees, that will be 0. So now here, the only relevant forces are the ones that are parallel to the surface. So which is they are parallel to the surface of this incline here. So now, what is it that we're going to do? So what we're going to do is, we're going to say, okay, how many of these forces? The obvious ones, the one that is parallel to the surface is force applied, that is our first. The second one is frictional force, which is pulling in opposite direction. The third one now, which is what most students tend to find to be tricky is the component of gravity that is parallel to the surface. Because gravity have two components. One, this one here, and the other, which is parallel to the surface. So this is FG perpendicular, and the C1 here is FG parallel, this down component. So now these forces, the three forces that are parallel is friction, is force applied that are parallel to the surface, and the component of gravity that is parallel to the surface. So now, if we're talking about the net force, which means we are talking about this force and these two forces, it's three forces in total. So now, so we want the work net, which is now, we're going to sum the forces, the work done by the forces doing the work here. So now we have three forces, so we're going to have work net is equal to the sum done by the frictional force, work done by force applied, and work done by FG parallel. Let's go to that. So now, work net is equal to work done by force applied, because it's parallel, plus work done by frictional force, because it's also parallel to our surface, plus work done by FG parallel, not FG, not just force of gravity, but it's the component of force of gravity, which is always downwards on your incline. So if your slope was inclined like this, that component will always be there. It will be on the opposite direction, or it will be downwards of the slope. And we know that the net force, okay, so now we can go to the next page. So we said the work net is equal to 0, because we said if the velocity is constant, the acceleration is 0. And if the acceleration is 0, which means the net force is 0, because the net force is the product of the mass and the acceleration. And if the net force is 0, the work net is 0, because the work net is the product of the net force and the displacement. So it is equal to work done by force applied plus work done by the frictional force plus work done by FG parallel. And now to work on this, so okay, 0 is equal to work done by force applied, which is what we want, plus work done by the frictional force. So the work done by frictional force is frictional force times displacement, right? But the frictional force, the motion is up the slope, right? And the frictional force is downwards, so it's opposing our motion. So we're going to give it a negative sign here. Plus work done by FG parallel. Our motion is up the slope, FG parallel is pulling down. So now what we're going to have is negative FG parallel times delta x. So it's negative because it's in the opposite direction of our motion. Okay. So now what do? We say, okay, we can simplify this. 0 is equal to WFA minus FF delta x minus FG parallel delta x. So what is FG parallel? FG parallel is equal to, I'm not going to derive it here, mg sine theta. It's defined as mg sine theta. Sine theta of what? Of that triangle that we're working on. Of this triangle here. So it's this angle here. We had our B here, and C here. So we had this point to be 13.12 meters. So now, our delta x, what is it? Is this displacement here? It's the distance between B and C. How are we going to find this distance? We were told that the velocity from B to C is constant. Or what? The speed is constant to be 2 meters per second. And we're told that it took 15 seconds to move from this point to that point. So which our time is equal to 15 seconds. Right? So we know distance is equal to speed times time. Our speed is 2 meters per second and our time is 15. Which is, this is 30 meters. So this point here is 30 meters. We have that displacement to be 30 meters, right? So now we go back to this. We have the frictional force. We're told that the average frictional force up the incline is 50 newtons. We have our displacement. We can find Fg parallel m, gravity, g, m mass, g, gravity. Sine theta is opposite over hypotenuse. You know it from maths. Or you can calculate the angle if you want to, but I'm not going to do that. Times the displacement, which is 30. And then we're going to find this. So, at this point, you say, okay, 0 is equal to WFA minus FF, which is 50, times 30, minus FG parallel times delta X. FG parallel is this, M, which is 200, G, which is 9,8, sine theta. Sine theta is called opposite, which is 13,12 over hypotenuse, which is 30, times 30. Oh, permanent marker. Shit. So this and that are gone. So you're left with this. So 0 is equal to WFA, work done by the applied force, minus this and this, 1,500 minus this time that. That's what we need to get now. 200 times 9,8 times 13.12. 25,715.2. You add these two. So 0 is equal to WFA minus 27,215,20 joules. So this is the work. Oh, sorry. Then you transpose this. WFA is equal to 27,215.2 joules. So this is the work done by the applied force. But that's not what they wanted. What they wanted from you was the power. What is it? The power delivered by the engine to move the car from point B to point C. So they want the power of the engine, which is the work done by the engine. So we said that the work done by the engine, the power is equal to the rate at which work is done. Work done by force applied over time. The work done by force applied is 27,215.20 joules divided by time. It took 15 seconds to go up there. So the power is equal to this divided by 15, which is 1,814.35 joules per second. And these are equivalent to watts. Or watt, I don't know. So 1,814.35 watts. So this is your power. This is how you do this question. I hope you understood it. If you don't, you have questions, or there are things that are very unclear to you, you can drop the questions on the comment section. I will try to address them as much as I can. Thank you for watching. Goodbye.